Welcome friends. Let us continue to study heat engines on my YouTube channel. Kindly like, share and subscribe my YouTube channel. The topics included in today's lecture are construction and working of Otto cycle and efficiency of Otto cycle. So Otto cycle, which is the air standard cycle, and it is a reciprocating engine. So this one is the cylinder, this one is the piston, and working medium air is filled up inside the cylinder. Now let us draw the PV diagram. So that is the PV diagram, and this condition is known as the initial condition. So it is state number 1, and at state number 1 pressure is P1 and volume is V1, and V1 is equals to V total. So we know that this is the total volume of cylinder. So V1 is equals to Vt is equals to total volume of cylinder. Now piston moves from right hand side to left hand side and reaches to the state number 2. And at state number 2, the pressure is P2 and volume is V2. The pressure of air, that is the working medium, has increased and volume of air, or that is working medium, has reduced. So that is nothing but the point number 2 or the state number 2, and that is the V2. And as the piston is at the dead center, that is the inner dead center, now piston cannot move towards the left, and so this volume is the clearance volume. So V2 is equals to Vc, that is equals to clearance volume. And the process number 1 to 2 is known as the isentropic compression process. So we say that the working medium air has passed through the isentropic compression process. Now let us see. We are supplying heat when piston is at point number 2. So it is known as the heat supplied, and heat is supplied at constant volume because at that time volume of air, that is working medium, does not change. So it is a vertical line 2 to 3, and heat is supplied, and 2 to 3 process is known as the constant volume heat supply process. So we can say that at point number 3 pressure is P3 and volume is V3, where V2 is equals to V3. So we can write down here V3 is equals to V2 is equals to Vc is equals to clearance volume. Now piston moves from your left hand side to right hand side, that is IDC to ODC, and reaches to the point number 4 or state number 4, and that at state number 4 pressure is P4 and volume is V4, such a way that V1 is equals to V4, and that process is known as the isentropic expansion process. So process number 3-4 is the isentropic expansion process, and it is in such a way that V1 is equals to V4, and therefore V4 is equals to V1, that is equals to Vt is equals to total volume of cylinder. Now next is the heat is rejected. Now heat is rejected in such a way that the volume of air does not change, and so it is a constant volume heat rejection process. So it is 4 to 1, and it is known as the constant volume heat rejection process. And after passing through 4 processes, the working medium, or the, you can say, system, reaches to the original condition, that is condition number 1. And we know that R, that is the compression ratio, is equals to Vt by Vc, that is total volume of cylinder divided by clearance volume of cylinder. So what is the total volume of cylinder? So it can be V1 or V4, and Vc can be V2 or V3. So we can write down R is equals to V1 by V2, or that is equals to V4 by V3. Now we are going to draw the TS diagram of the air standard cycle. We have already done, you can say, PV diagram. So let us start with the PV diagram. At point 1, pressure is P1, volume is V1, and temperature is T1, and entropy is S1. Now it passes through the isentropic compression process. 1 to 2 is the isentropic compression process. Now as it is the isentropic compression process, the it can be drawn as a vertical line on TS diagram, because S is the entropy and S is a constant entropy drawn by the vertical line. So 1 to 2 is the isentropic compression process where the entropy is same, that is S1 is equals to S2, and temperature at point number 1 is T1 and temperature at point number 2 is T2. Then it passes through the next process, that is the constant volume heat supply, process number 2 to 3. So that can be drawn by the curved line on TS diagram. This 2 to 3 is the constant volume heat supply, and at point number 3 temperature is T3 and the entropy is S3. Now it passes through the next process, that is process 3 to 4, that is known as the isentropic expansion process. So as it is an isentropic expansion process, entropy remains constant. Again, due to that, it is shown by a vertical line from the point number 3. So it is 3 to 4 is the isentropic process, and at point number 4, the temperature is T4 and entropy is S4. And we know that as 3 to 4 is the isentropic process, S3 is equals to S4. Last process is constant volume heat rejection, 4 to 1 process. So it can be drawn by the curve on the TS diagram where heat is rejected. Now heat supplied. Now heat is supplied during which process out of 4 process? Yes, heat is supplied at the second process, that is process number 2 to 3, and it is constant volume heat supply. So what is the equation for the change in you can say heat for the constant volume process? So here we have to remember or recall the fundamental of the chapter properties of gas. And for constant volume process, the equation for heat transfer, that we have to recall and put it here. So for this, heat supplied is equals to mCV delta T, right? So CV into delta T. Now what is the temperature difference here? So here the temperature difference is T2 minus T3. T3 is higher temperature, T2 is a lower temperature. So it is mCV T3 minus T2, that is heat supplied equation. Now next is the heat rejected, QR. Now let us see during which process heat rejection takes place. Let us find out. Yes, during process 4 to 1, the heat rejection takes place. And the process name is constant volume heat rejection. So we have to put here the equation for the heat transfer for the constant volume process. So again it is same, that is mCV delta T. But here delta T means temperature difference is for the process 4 to 1. And so it is T4 minus T1. So QR is equals to m into CV into T4 minus T1. So we have got the QS and QR. Now let us calculate the work done. So work done is equals to QS minus QR. Substituting these two values and taking out common. So which parameter are common? M and CV are common. So we are taking out common M into CV. So into bracket T2 minus T3 minus T4 minus T1. That is the work done during Otto cycle. Now let us calculate the efficiency of Otto cycle. And that efficiency is known as the air standard efficiency of Otto cycle. So that is equals to work done upon heat supply. Work done equation we have already calculated. Heat supply we have already found. So putting the value M into CV into T3 minus T2 minus T4 minus T1 divided by M into CV into T3 minus T2. So which term can be cancelled from numerical and denominator? Yes, it is M into CV. So the answer is T3 minus T2 minus T4 minus T1 divided by T3 minus T2. Again, this T3 minus T2 term can be cancelled. So the answer is 1 minus T4 minus T1 divided by T3 minus T2. That is known as the air standard efficiency equation for the Otto cycle in terms of temperature. It means if we know the temperature of all 4 states, we can calculate the efficiency of Otto cycle. Now let us again, you can say, simplify the equation. Process number 1, 2 is known as the isentropic compression process. And using the relationship between PV and T for the isentropic process, we can write down T2 by T1 is equals to V1 by V2 raised to gamma minus 1. Now what is V1 by V2 for our case? It is R, that is compression ratio. So we can write down T2 by T1 is equals to R raised to gamma minus 1. And so we can write down T2 is equals to T1 multiplied by R raised to gamma minus 1. Now let us study the process number 3 to 4, which is isentropic expansion process. Again writing the relationship between PV and T for the isentropic expansion process, that is 3 to 4, is T3 by T4 is equals to V4 by V3 raised to gamma minus 1. Now what is V4 by V3? V4 by V3? Yes, V4 by V3 is R, that is the compression ratio. So we can say that T3 by T4 is equals to R raised to gamma minus 1. And so that we can say that T3 is equals to T4 multiplied by R raised to gamma minus 1. So we have found the equation for T2 and T3. Now let us substitute the equation of T2 and T3 in the equation of air standard efficiency. So it will be 1 minus T4 minus T1 in the numerator as it is divided by, instead of T3 we can write down T4 multiplied by R raised to gamma minus 1 minus, instead of T2 we have to write T1 into R raised to gamma minus 1. So now what is common in the denominator? That is R raised to gamma minus 1. So take it out. So it is 1 minus T4 minus T1 divided by R raised to gamma minus 1 multiplied by T4 minus T1. So what can be cancelled? This bracket can be cancelled. And so our efficiency of Otto cycle, that is the air standard efficiency of Otto cycle, that is equals to 1 minus 1 upon R raised to gamma minus 1. Now you look at this equation. Here efficiency of Otto cycle depends upon two parameters. One is R, that is the compression ratio. Another is the gamma, that is adiabatic index. And for air, the gamma value is constant, that is 1.4. So we can say that efficiency of Otto cycle depends on only R value. Clear? And as the value of R increases, the efficiency of Otto cycle also increases. And after some point of time, the increment is very less. And due to that, it is said that the typical value of compression ratio for the Otto cycle is in this range. So that is the air standard efficiency of Otto cycle. So as the compression ratio increases, thermal efficiency also increases. However, there is a limit on R depending upon the fuel. Due to high compression ratio, the temperature of fuel may increase during compression process and it may ignite the fuel in advance, causing the coke. Kindly ask your queries in the comment box. Kindly like, share and subscribe my YouTube channel. Thank you.